Volumes. Suppose we wish to find the volume of a non-uniform solid. So look at the picture we have here. We have some sort of a solid shape here, and it runs along the x-axis from x equals a to x equals b, and we want to find the volume of this solid. So what we're going to do is take a slice of this volume here, perpendicular to the x-axis, and when you take that slice, you will get a piece of the solid here, almost looks like a piece of bread, and let's assume that we can find the area of that shape, the cross-sectional area. If we then take that cross-sectional area and multiply it by the thickness, that will give us an approximate volume for this slice. Now, of course, what we'll end up doing is we'll take lots of slices of this solid, and you can see that each piece or each slice is different from the one next to it, but not significantly so. So if we can find the volume of all of these little slices, we can add those up and get an approximate volume for the solid. So the definition of a volume, let S be a solid that lies between x equals a and x equals b if the cross-sectional area S in the plane PX perpendicular to the x-axis at x, if that area is a of x and a is a continuous function, then the volume of the solid can be expressed by taking the limit as n goes to infinity of the sum of the cross-sectional areas multiplied by the thickness. And of course, this is a Riemann sum, and when you take the limit of a Riemann sum, it becomes a definite integral. So the bottom line is this: to find the volume of a solid, if you can take a slice of that solid and find the cross-sectional area of that slice, you're just going to integrate that cross-sectional area with respect to x from x equals a to x equals b, and this will produce the volume of the solid. Let's take a look at an example. Here we want to find the volume of a pyramid whose base is a square with side length capital L, and whose height is h. So h measures from the tip of the pyramid all the way to the base. Now you'll notice that this pyramid is turned on its side, and we do that on purpose because when you turn a pyramid on its side and you run along the x-axis, the cross-sectional slices of that pyramid are all squares. And so if we look at that pyramid in a two-dimensional setting here, this right here represents this slice. And so if we wish to find the area of this cross-sectional piece here, we need to find the length from here to here, because this length represents the length of one of the sides of this square. So to find out what S is, I'm going to use the fact that this triangle here and this triangle here are similar triangles. And because they are similar triangles, we can set up a proportion with their sides. So we can say that the length from here to here, which is S, that will compare to the length from here to here, which is x, the same way that the length from here to here, which is L, will compare to the length from here to here, which is h, the height of the pyramid. And with this now, we can solve for S. S is going to be L over h multiplied by x. So all I'm doing here is multiplying both sides by x. Now keep in mind that L and H are both constants, so we now have the side of this square here expressed as a function of x. So if we come over here, the area of that cross-sectional piece we know is basically just side times side, or side squared. And since we now know that the side is L over H times x, all we have to do is square that to get the area. And so our area function is L squared over H squared times x squared. Now to get the volume, we are simply going to take the integral from a to b of that cross-sectional area with respect to x, and that is the integral from x equals 0 to x equals h of the cross-sectional area, which is L squared over H squared times x squared times dx. Now let's keep in mind that this here is a constant with respect to x, so that can be factored out of the integration. And now we just need to find the antiderivative of x squared, which of course is x cubed over 3. And then we'll evaluate that from 0 to h. And so we have L squared over H squared times H cubed over 3 minus 0 cubed over 3. And 0 cubed over 3 is 0. And so this becomes L squared H cubed over 3h squared. And then finally we can cancel the h squared here with 2 factors of h there. And we get L squared h divided by 3. Most of the volumes that we calculate in this course will be volumes obtained by revolution. So let's take a look at this next example. Find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals the square root of x from 0 to 1. And then we want to illustrate the definition of volume by sketching a typical approximating cylinder. Okay, so first of all, we have our function y equals the square root of x equals 0 to x equals 1. So we're taking this area under the curve and we are rotating it around the x-axis. And when you do that, this is the volume, or I should say, this is the solid that results. And we wish to find the volume of that solid. So when you do a volume from revolution, every time you take a cross-sectional piece of the graph, that is going to be circular in nature because you are revolving it around the axis there. So that disk right here will have a radius associated with it, which I will call r. And we know the area of the disk is simply equal to pi times r squared. So all we really need to do here is figure out what is r. And in this case, it's very simple because r is the distance from the x-axis up to this point. And let's keep in mind that this point is corresponding to the point here on the curve, which is y equals the square root of x. So if we are at a particular x value here, the distance from the x-axis up to this point is, of course, the y value, which is the square root of x in this case. So the area here, which we know is pi times big R squared, is going to be pi times the square root of x squared. Because again, that radius is simply the function square root of x. So if we do the math here, we have pi times x, and now the volume is just going to be the integral from x equals 0 to x equals 1 of the area function, which is pi x dx. Pi, of course, is a constant, and so that can be factored out of the integration process. And we end up with pi times x squared over 2 from 0 to 1. And this is pi times 1 squared over 2 minus 0 squared over 2. And of course, this is simply going to be pi times 1/2, which is pi over 2. So for all of these volumes of revolution, we're going to be finding the volume of a cylindrical disk, if you will. And so to do that, we need to find the area of the disk, which is always going to be pi r squared, and then you multiply it by the thickness, and that's what gives you the volume. Let's take a look at another one. Here we want to find the volume of the solid obtained by rotating the region bounded by y equals x cubed, which is this function right here, y equals 8, which is this line, and x equals 0, about the y-axis. So we are going to take this region in here, and we're going to rotate it about this y-axis here. And when you rotate it around, you will form a solid that looks something like this. Now again, I want you to notice that when you rotate that around and you take a cross-sectional piece, this of course is going to be a disk again. And so we know the area of that disk is going to be pi times the radius squared. So the only question is, what is this radius here? Well, if you think about this point here as being the point xy, clearly this radius is equal to the x coordinate of that point, right? As you can see down here on the x-axis is the number x. But here's the thing. These disks start down here and they run along the y-axis. So in other words, if I were to draw more of these disks, right, they would look something like this. So these disks are clearly running along the y-axis, which means we are going to be integrating not with respect to x, but with respect to y, because they begin down here at y equals 0, and they end up here at y equals 8. So even though it is true that the radius of this disk here is x, we need to remember that this point is on the curve y equals x cubed, and if you solve that for x by taking the cube root of both sides, you get x equals the cube root of y. So the radius, again, which we know is x, we're going to express that as the cube root of y because, again, that point is on the curve, x equals the cube root of y. Now, I'll just pause for a second here and say that finding r is the most challenging part of these problems. Once you have r, you pretty much have the problem solved. So once we have that r value there, we're going to say the cross-sectional area, which is going to be a function of y, is going to be pi times r squared. In this case, that is pi times the cube root of y, quantity squared. And so the area function as a function of y is going to be pi. And then the cube root of y squared, let's remember that that is the same as y to the 2/3 power. And so now the volume will be the integral from 0 to 8 of pi times y to the 2/3, and we are integrating with respect to y. Let's do the math here. We have pi antiderivative will be y to the 5/3 divided by 5/3. Let's go ahead and invert and multiply. So we have 3/5 y to the 5/3, and let's not forget our pi here. And then we're going to evaluate this from 0 to 8. So I'm going to say this is 3 pi over 5 multiplied by 8 to the 5/3 minus 0 to the 5/3. And this is 3 pi over 5 times, what is 8 to the 5/3? Well, remember it's the cube root of 8, which is 2, and then 2 to the 5th power is 32. And 0 to the 5/3 is 0. So finally, we end up with 96 pi over 5. Next, let's take a look at the region R enclosed by the curves y equals x and y equals x squared. And we're going to take that region and rotate it around the x-axis. And we want to find the volume of the resulting solid. So the difference here is that when you take this region and you rotate it around the x-axis, you can see the solid that you create here. But most importantly, when you take a look at that region, that little rectangle, when it gets rotated around the axis here, it creates what we call a washer. And a washer is just a disc with a hole in the middle. Okay, so there is a hole here. So how are we going to find the volume? Well, again, we need to find the cross-sectional area. So here is that washer in 2 dimensions. And if I want the area of just this part, the way I'm going to do that is I'm going to take the area of the whole thing and I'm going to subtract the area of the inside part. Okay, so to get that cross-sectional area, I'm going to take the area of the large circle minus the area of the small circle. So when you think of large circle and small circle, the large circle we will say has a radius of capital R, and the small circle we'll say has a radius of little r. Now, what is big R and little r? Well, again, let's come back over here to our curve. So when you rotate that around, big R is the distance from here down to here. So this is big R. And you should see that for this particular value of x, that distance is going to be the y value on this function, which coincidentally is also x because this is the function y equals x. So big R is equal to x. Little r is the distance from here to here. Okay, so this is little r. And that distance is simply the y value here, but that y value comes from the curve y equals x squared. And so if we're at some value x here, the y value here is x squared. And so little r is x squared. Okay? So your area of the large circle is going to be pi times big R squared minus the area of the small circle is pi times little r squared. And now we know big R is x and little r is x squared. And so what we get is pi x squared minus pi x to the 4th. And that is the cross-sectional area of this washer. And so now once we have that, the volume is simply the integral from 0 to 1. Remember, you got to go from x equals 0 to x equals 1 because this corresponds to the point 1, 1. And we're going to have pi x squared minus pi x to the 4th with respect to x. Now, usually what we'll do in these cases is we'll just factor out the pi here. So we get pi integral 0 to 1, x squared minus x to the 4th. And then we'll go ahead and take the antiderivative. So we get x cubed over 3 minus x to the 5th over 5. Again, from 0 to 1. And finally, we'll plug in 1. And I'll skip a little bit of the work here. We should get 1/3 minus 1/5. And of course, when you plug in 0, you get 0. And this is going to be pi times 5 over 15 minus 3 over 15, which is 2 over 15. And so our final answer here is going to be 2 pi over 15. So again, I'm not worried about this part. This part is relatively simple. It's all about identifying big R and little r. So let's summarize what we just did in that previous problem. Suppose we have two functions, f of x and g of x, that enclose an area. And let's suppose we're going to take this area and revolve it around the x-axis. If you take a look at a sample rectangle within that area, when that rectangle gets revolved around this axis, there will be a mirror image of that rectangle down below here. And of course, this is going to create a washer, as we just discussed a minute ago. Okay. Now, if you take that washer and you lay it out flat over here, you will have a disc with a hole in the middle of it. All right. So what we need is the big radius, capital R, which in this diagram here is the distance from here to here. And then we also need the smaller radius, little r, which is the distance from here to here. So in this particular case, big R would just be f of x, and little r would be g of x. But again, the main concept here is that the cross-sectional area is going to be pi times big R squared minus pi times little r squared, or we can write this as pi times big R squared minus little r squared. And then the volume is the integral of this. And then normally what we'll do is we'll factor out the pi and we'll express it in this way. Okay? But then we have to understand that big R and little r are some function of x. So again, in this case, big R is f of x and little r is g of x. But that's not always going to be the case. So there are ways that we can complicate this, and I want to speak a little bit about that as well. What if we were not rotating this region about the x-axis? Let's instead assume that we were rotating it around some line up here. So let's call this line y equals a. No, not y equals a. That's a bad choice because our limit down below is a. Let's call it y equals L, okay? Now, when you rotate around this line, you're no longer getting this shape down here. You're taking this rectangle and you're rotating it around this way. So when you do that, the mirror image of that rectangle is now up here, and the disk that you get is this way, okay? And then now your big R is completely different. Your big R is the distance from the center of the circle to the farther end of the rectangle. So it's this distance here, that's big R. And the distance from here to here, that would be little r. And then you have to compute those distances by subtracting functions from this value L. So I don't want to get too much into it in this particular shape, but the point is, a simple diagram can go a long way in helping you determine big R and little r. But big R and little r are not always just going to be the given functions. Sometimes they are more complicated than that. So in the next example, let's find the volume of the solid obtained by rotating the region in the previous example about the line y equals 2. So here is the region from the previous example that we just did. Now what we're going to do is rotate this region around the line y equals 2, which is up here somewhere. So let me go ahead and bring y equals 2 into the picture. So here is y equals 2. So we are taking this region here and we are rotating it around that line. And when you do that, you can see that you're going to get a solid that looks something like this. Now, what I want to stress to you here is that you do not have to be an artist. You do not have to be able to draw the solid to understand what's going on here, okay? But I have available for you a nice picture to kind of show you what that region would look like. But again, notice that you have a washer here. So all you need to do to find this volume is you need to determine what is big R and what is little r. Once we have those, then we can pretty much just plug it into the formula. So let's dig deeper here and try to figure out what big R is and what little r is. So big R is the distance from the axis of revolution, which is y equals 2, to the farther end of the region. So remember, there's a representative rectangle here, and when that gets rotated around this line, you're going to have a mirror image of that rectangle up here, and big R is the distance from the axis, which is right here, to the farther end. So that's big R. And then little r is the distance from the axis to the closer end of the rectangle. Because again, if you look at this diagram over here, you can see big R, right? Big R is the distance from here all the way down to the bottom, and little r is the distance from here down to this curve. All right, so what are those distances there? Well, when you're finding a vertical distance, such as big R here, all you have to do is take the top function minus the bottom function. So the top function here is y equals 2. The bottom function is y equals x squared. And so it's just going to be 2 minus x squared. And then little r, same idea. We're going to take the top function, which is y equals 2, and we're going to subtract the bottom function, which this time is just y equals x. So it will be 2 minus x. All right, so once I have big R and little r, now I know the cross-sectional area, which is pi times big R squared minus pi times little r squared, is going to be pi times 2 minus x squared quantity squared minus pi times 2 minus x quantity squared. And so the resulting volume will be pi integral from 0 to 1 of 2 minus x squared squared minus 2 minus x squared. Okay? And so now we just have to multiply this out and compute everything carefully. And again, this should be the easy part of the problem, but don't take anything for granted when you're doing this. Make sure that you go slowly and that you take your time. So let's go ahead and go through it here. We have pi integral 0 to 1. We're going to multiply this out. I won't show the work here on camera, but I'm just multiplying out that polynomial there. Minus, and then we'll multiply this polynomial out. And then next, we're going to go ahead and distribute the negative. And then after that, we'll combine like terms. So we have 4 minus 4x squared plus x to the 4th minus 4 plus 4x minus x squared. Let's point out that 4 minus 4 cancels, and negative 4x squared and negative 1x squared is going to be negative 5x squared. So we have pi times the integral from 0 to 1. I have negative 5x squared. I have positive x to the 4th, and don't forget also positive 4x. Now that it's simplified, we'll go ahead and take the antiderivative. So we have negative 5x to the 3rd power divided by 3 plus x to the 5th power divided by 5 plus 4x to the 2nd power divided by 2. And we'll evaluate this from 0 to 1. Now the nice thing here is that when you plug in 0, you get 0. So all we really need to do is plug in 1. And so when we do that, we're going to get pi times negative 5/3 plus 1/5 plus, and then this is just 2x squared. So when x equals 1, we just get 2. And then let's go ahead and get a common denominator, which is going to be 15. So we have negative 25 over 15 plus 3 over 15 plus 30 over 15. And this ends up being 8 pi over 15. In our final example, we are going to look at the same region from the example 4, which is this region right here. But now we're going to rotate it about the line x equals 1. So let's think about that. Excuse me, x equals -1. X equals -1 is over here. So here is that line. And when we rotate this around here, now our rectangle is not going to be this way. It's going to be sideways. So ignore that rectangle. And let's draw one sideways here. Okay. You always have to draw your rectangle perpendicular to the axis of rotation, because when you rotate that around, you're going to get this disc that you can see here. All right. So again, we need to know what is big R and what is little r. Big R is the distance from the axis of rotation all the way over to the farther end of the rectangle. That's big R. Little r is the distance from the axis of rotation to the closer end of the rectangle. Now, these are horizontal distances. And when you find horizontal distances, you need to take the right value and subtract the left value. And because we're doing things horizontally, everything is going to be in terms of y. Okay? So instead of thinking of the function y equals x, think of it as x equals y. Same thing here. Instead of thinking of the function y equals x squared, think of it as x equals the square root of y, right? Because if you solve for x there, you get x equals the square root of y. So when I'm looking for big R here, big R is going to be the value here, which is on this function. So that's going to be the square root of y, minus the value over here, which is -1. So it's literally the square root of y minus -1. Little r, same idea, is going to be the value here, which is x equals y, minus the value over here, which is -1. So big R is the square root of y plus 1, and little r is just y plus 1. And then along the y-axis, these all start down here at y equals 0, and they end up here at y equals 1. So coincidentally, we're going to have the integral from 0 to 1. I will assure you that the limits of integration are not always going to be 0 to 1. And then we'll have big R squared minus little r squared, and in this case, dy. And then just like in the last problem, we just need to multiply this out and then take the antiderivative and use the fundamental theorem of calculus. So we're going to have pi integral 0 to 1, y plus 2 times the square root of y plus 1, minus y squared plus 2y plus 1. Distribute the negative. Cancel out like terms there. Combine like terms here. So we get pi integral from 0 to 1. Y take away 2y is -y. Plus, then we have 2 times the square root of y, which will be 2y to the 1/2. And then minus y squared. Let's go ahead and find the antiderivative. Hopefully your antiderivatives are getting better so that I don't have to explain all those steps. And then the last thing we need to do here is, let's go ahead and simplify. So, I don't know, -1/2 y squared plus, this is going to be 4/3 y to the 3/2 minus 1/3 y cubed. So right here, in case you're wondering, remember, you have to be careful. We are multiplying by 2/3 there, right? Because when you divide by 3/2, you're multiplying by 2/3. So that's how I got this 4/3 here. And finally, from 0 to 1, once again, we don't really have to plug in 0 because you get 0 when you plug in 0. So we have negative 1/2 plus 4/3 minus 1/3. And this is going to be pi times 1/2, which is pi over 2. And that concludes this video lesson.